Cool. All right, let's welcome our next speaker, Rachit. Thanks.
Hey everyone, I'm Rachit. You might remember me from LatchUp 2 years ago, where I was fear-mongering about designing hardware and how you could be more fearless in doing this. This year, I'm sort of in this dual role. So I'm starting as a professor at MIT, but I'm also spending some time at Jane Street. And so I want to talk a little bit about the system they use called Hardcaml and how they use it internally, not really. And I want to do this in somewhat of a weird way, which is I want to show you how to build your own embedded HDL. So we've been hearing about different kinds of software-based HDLs. And I wanted to take the opportunity of showing you how you can build your own and one particular way of doing it that I think is pretty cool. And I'll show you how it connects to Hardcaml at the end. This is very much in a lecture style of a talk, because that's what happens when you invite professors to give talks now. So I promise, if you don't ask questions, it's going to be kind of boring. So feel free to just shout questions, heckle. Well, maybe that's not the best thing for me to do. But there's a mic that'll be running around. Does that sound good? People on board? OK, let's build an eHDL. And I'll start with this weird fundamental question of what is an adder, right? An adder is something. We'll start with sort of very basic, simple building blocks, and we'll start with combinational ones. And so the simplest one I can think of, is an adder, right? And an adder is something that takes two signals and returns a signal. I've not defined what a signal is, but we can write down its type. We can say an adder is something that takes signal L, signal R, and returns a signal. And I kind of leave the implementation undefined. I don't tell you how to build adders, right? It's kind of weird. I've left it abstract. But I can show you that even though you leave this part abstract, you can still do something useful with this definition of an adder. For example, you can take this function that represents the circuit adder and build a new function called constmul. OK? So I want us to pause for a second and try to read this code. It's kind of written in pseudo Python. And try to figure out what this function is computing. And I want someone to answer me. Yeah, back there. First, I think. So it's computing a multiply. OK, but what is it? Did you have a different answer?
Hang on, sorry. Let's run the mic. So otherwise, the video won't make sense.
Well, I mean, it's taking the signal and then multiplying it by a compile time constant. So it's not multiplying two signals together, but it's repeating it this many times, and you define it ahead of time.
Yeah, it's sort of an interesting answer. So the answer was it's multiplying it with some compile time constant. So there's something that represents the signal. And that signal is a circuit time value. It's a value that when you're executing your circuit, that value will show up only when the circuit is executing. But this value k is actually compile time. It exists in Python, right? So the way this code will work is when you call constmul, it's going to use the value of k and build a circuit for you by repeatedly calling the add operator on it. Remember, add is something that takes two signals. Have we given it the right input? Well, we have s here, which is guaranteed to be a signal. And then we have cursig, which is either s at the start, or it's add, which again returns a signal, right? So it's building a little circuit. And so this is really the magic of embedded DSLs, which is that you have some things inside the language, like this thing called an add, which is somehow building circuits for you. Again, I've not explained to you how it does that. But it builds those circuits for you. And then you just get to use the host language, the software language you're working in, to build that circuit for you. So using add, you can define higher level functions or libraries like constmuls, right? Your language could be Python, and that's what PyMetal or Pertl is. You could be Scala, and that's what Chisel is, although Chisel does it slightly differently, I think. And you could do it with OCaml, which is what I've not shown you, but that's what happens in Hardcaml. So the big point to take away from this is that eHDLs, there's some sort of recipe going on in building one of these, which is I should I think your answer was getting at this, which is that what the circuit we're building looks something like this. It's sort of a chain of, and the critical path is going to be terrible. You're right, right? So this is a bad circuit, but it's a circuit nonetheless, and you can build better circuits potentially. So this is what it computes. But the recipe of building embedded eHDLs or embedded HDLs is you define some small set of primitives, things like that look like adds or subtract, even registers if you're feeling a little adventurous, and you use the features of the host language to build the rest of the library. So you look at the API of Chisel or Hardcaml or Pymetal or something like this, and it's a massive API, right? And you look at it and you're like, goddamn, how am I supposed to implement something this huge? Well, you don't have to. You can build most of it in the software language itself as long as you define the small set of primitives. So that's one thing I want you to take away. And so like you have lots of different functions that are going to use your building blocks. The building blocks are in orange. The higher level functions are defined on top of it in lilac purple. Does this all make sense to people, which is like you start with small building blocks and you can build a big library. So we've seen what happens from the middle up. Now let's look what's inside a signal. Okay. Again, what's an add? Well, it takes two signals, produces an output. But if we think about it, what values can L be? What can be on the other side of that L? Well, it could be a constant. It could be some value. It could be a wire or a register. Or it could be some other more complex circuit behind it, right? And really, that's it. That's about all of the things that L can be on that side. So now we're thinking about how to actually implement that signal type that we were seeing in the past. And again, it's not too hard. You just need those three things to be represented. And you can define a signal type. So here's how you build the signal type. Or here's one way of building it, which is you define some struct. It's called signal. It has a name, some sort of identifier so that you know what it is and some way of uniquely identifying it. And some type that contains information like, oh, it's a constant. What value does it have? It's a wire. Who is driving it? Is it a register? Like, again, who's driving it? Or like if it's a circuit, well, what are its own dependents? So some examples of struct types are like 0 is represented by the name 0, and a constant which contains the numerical, like Python level value 0, let's say. Similarly, a clock is just a signal named clock, and it's a wire. It's sort of floating in the ether. At some point, it'll get connected, but sort of sitting out there. Something like add, now we can define as a function that takes the two inputs, which are themselves signals, and it puts it into this type called a primitive add. Yeah, what's up?
What up? Sorry.
Why do we need to assign names to these signals? Why can't we just use the variables in the host language to deal with that?
That's a great question. So the question is, why do we need names? It's like, you have a name right there. Why are you making me write a name right here, right? The problem is, it's not really a problem, but the way we build this embedding, the language, the sort of HDL language, is everything on the right side of that equal to sign. Clock is just the name in the host language. For example, the way this works in Hardcaml, we have like basically a preprocessor pass that allows you to do exactly what you're thinking about, which is you say clock equals to signal just wire and no clock in it, and it'll copy that name for you. But by default, you can have clock 0, clock 1, clock 2, and you can give it the same variable name. So there's a separation going on, again, the world between the host language, which again is Python, and the object language, the circuit language that we're constructing on the right side. Does that make sense? Sweet. Any more questions? While I unlock my iPad. OK. Add is kind of, it's weirdly simple. It's just like some identifier that tells that this node is an add, and pointers to the other nodes that exist beyond it. And so really what we're doing is we're constructing a computational graph. We're building sort of the structure of our circuit, and we're capturing it by connecting things together with this like signal representation. For those of you who are interested or might already know about this, this is exactly how languages like PyTorch or TensorFlow work. They sort of capture the computational graph that you write down that represents your machine learning kernel, and then compile it or execute it in a runtime and so on. That's a little bit of a lie. They do a little more, but functionally about the same. Sweet, 5 minutes left. Once we have this representation, we have to go to the final step, right? We've captured this computational graph, but we actually need to generate RTL. That's the whole point of having an eHDL. We want RTL. And so we'll build what I'll call a syntax-directed compiler. This is sort of the baby's first compiler way of building a compiler. And the way you do it, again, I'm using some made-up syntax here, is you take a signal, and you say, I'm going to take the signal, produce RTL. And RTL is just strings, OK? And the way I'm going to work with it is I'm going to take the signal, and this would really be signal.type. If the type of the signal is some constant value, I'm going to just return the string be, quote, the constant. This assumes that the constants are represented in binary. If I have, for example, the more interesting case of an adder, I'm going to compile the left side, compile the right side, and I'm going to emit a string that represents the rest of the circuit. And so you recursively compile the structure. And again, because you've sort of collected this big computational graph, you can just recursively go down, compile each component, combine them up, and you get a circuit. Is this very readable? No, right? So when Jack was mentioning that there's a lot of work that goes into making it readable and useful for people, that's where it happens, right? If you actually dump out this code, no one can read your Verilog and actually use it. But again, that's about it. So an HDL program starts with some set of high-level operations on it, right? Things like constml and other APIs that are defined in terms of basic building blocks like add, which are then compiled to RTL. And so now you know how to build an eHDL. I hope to see 100 new eHDLs by tomorrow. Okay.
Please no.
The problem is that it's not really, the problem wasn't that you need an eHDL. The problem is you also need a lot of other tools. One of the big reasons that's nice to use languages like Chisel is that they give you a lot of nice new abstractions that are not available to you in Verilog. Right? So you want to build a simulator that can take your high-level language and give you error messages and simulation reports at that level of the language. You want to build verification tools or formal tools. Right? And it's a lot of work to build these tools. What I want to show you is that everything you've learned up till now actually makes it quite trivial to build new tools. And I'll do this by showing you in about one slide how to build a simulator with the exact representation. So going back to what the signal type that we looked at is, well, there's nothing sort of inherent in the way we've defined add that lends itself to being a circuit. We can define it to be a circuit, but we could define it or interpret it to be anything else. We could define it to be a little sort of function that when we call, it returns the result of our computation. Right? And so the basic insight is that once you have defined these base primitives, you can interpret them in different ways. The simplest interpretation is build a circuit. But another interpretation could be define the set of functions that are going to represent the result of simulating this, let's say, combinational sequence. So here's how you build a simulator for combinational components. You need a little more trickery for registers, but you should believe that this will work for combinational components. So you define a different signal type. And instead of having the field ID, it has a field called compute. Right? And it's a function pointer. And that function pointer captures what the computation that node is going to do is. So for example, if you look at the implementation of add, which again is one of these base primitives we've already defined, well, add is going to define its function as I compute what my left node does and what my right node does, and I just add the results. And so you can build, again, in this very nice syntax-directed way, a whole simulator. It's not going to be fast. It's not going to be great. But you could do those things by building different interpretations of your signal type. Right? And you need more functionality for registers, but hopefully you get a flavor of what it takes to build simulators out of the same API. So the basic sort of big insight I want you to take from here is if you do this correctly, you can define a set of base primitives, and all of your tools exist on this side. You can define your base primitives to be compiled to RTL, and that'll give you a circuit generator. Or you can define what they mean computationally, and that'll give you a simulator. Or formally, and that'll give you a formal validator. And you can just build high-level libraries and not have to worry about this step, because the base primitives are sort of the interposing step that allow you to do this. The trade-off is the larger your base primitive library, the more control you have on how exactly the RTL is generated or simulated, but the more work you have to do to build each tool. This very final part, I want to show you why this talk is titled about Hardcaml. Hardcaml is a realization of precisely this idea. So here is the base types of Hardcaml. Just to give you insight on how many you need to build a combinational component of the HDL, you define these, 7 operators or so? And you can get an API that is this big. This is all open source. You can go look at the API. But all of these functions are derived from just these 7. And so you can build this really big API. And every time you implement this comb.inf.primitives shape, you get a new tool out of it.
Can you just zoom in on one of those?
Yeah.
Down the bottom in the, yeah.
Sure.
As an example of what you've done here.
So here's selections, LSBs, MSBs,
Oh, yeah, okay.
drop top, stuff like that. And there's tons of them. There's arithmetic operations. There's conversion operators, splitting, blah, blah, blah. All of these are defined in terms of the original stuff. And in addition to that, there's a simulator implemented in Hardcaml, again, using the kind of idea I've described to you. And there's actually several simulators. If you want really quick simulations for unit testing, we use something called CycleSim, which can sort of run inline, but is written in OCaml and sort of slow for big designs. But we also have CycleSim_Verilator, which will compile your design, again, by compiling those 6 primitives I showed you at the top, roughly speaking, to get verilated components that you can simulate. And Hardcaml has a ton of different things and features implemented. These are all the modules. And so if you're curious about Hardcaml or want to learn more about it, I encourage you to check it out. But hopefully this style of building DSLs has been useful for you to learn and think about. That's it.
Thank you. OK, thank you. That was a very good talk in the sense that it broke down really what all these DSL HDLs are doing, which is that they're kind of redefining the primitives, right, and playing around with that very cleverly, and also leveraging the host language as a fancy generate loop, basically, for all of this stuff. In your opinion, what is the killer feature that is causing everyone to write their own DSL these days? Is it the redefinitions of the primitive, or is it the host language, or is it this combo of the two, which just makes it irresistible for everyone to just go and play with?
Yeah, that's a good question. It's sort of trying to figure out why people care about eHDL so much. So embedded HDLs, people have been thinking about and building since the 80s, but they've become really popular recently. And I have my answer. Different people have different answers. I think the capability of, again, building reusable generators, which was, again, really popularized by the Berkeley efforts on the Chisel language, made it evident that you could build really big designs by building small blocks and composing them. I think the one other thing that drives people to build their own HDLs is they might fit really neatly with the existing infrastructure. So Jane Street, for example, uses a lot of OCaml and has a really mature OCaml testing, verification, validation stack. And so it makes a lot of sense to be able to write OCaml so that we can, for example, take engineers on a different team, have them contribute some function that they might really care about, and we write the shell that allows them to accelerate their computation.
And can I ask, without giving away too much information there, is the goal to abstract what used to be in software in hardware?
That is sort of, I think, the intellectual goal. Whether it is happening in practice at any company, I really doubt, because I think one of the sort of things that I don't really believe that comes from the HLS side of research and work is that you can just take software design and turn it to hardware designs. I think hardware design fundamentally requires people to understand structure and timing in a way that if you don't, you can't build fast hardware. And so there is work. Maybe it reduces the amount of friction that it takes. I do think the ability to rapidly iterate and build sort of these libraries and tools is a value add. But I think one of the really tricky things, for example, for us and for people broadly, and showed up in the Chisel update too, is like, how do we verify these massive compositional parameterized generators? I think that's sort of one of these untapped, really hard, unsolved problems.
Yeah, cool, yeah.
In your slides, you said circuits are computational graphs, but I believe it's computational graphs with states.
Mm-hmm.
So can you briefly explain that?
Yeah. So the question is, I showed you this like nice lie about pure computational graphs. You just compose them and you're done. But really, circuits have state, and that's the other part of the equation I didn't show you. Hopefully, you can believe me on fiat that you can define registers in the same way and compose them together. So what I am showing you is the combinational interface. Hardcaml defines this other type called signal.t, which has combinational components, registers, and memories. And those three things together make a full circuit, like hardware description language. And registers are also defined in exactly the way you think. They have a clock, clear, reset to, and so on. But once you define those like two other functions for registers and memories, you can get a full HDL. Good question.
Can I get one more question?
Please.
So does that mean someone else needs to provide highly customized implementations of primitives?
Yeah, so one of the cool things that I didn't get to talk about is that how you can take the signal type and you can annotate it to track more information. So for example, internally, one of the things I'm thinking about and building is clock domain tracking on the signal type. And notionally, you can think of the only change that I have to do is redefine those 6 primitives to track clock domains and give error messages when they mismatch. And all of the existing code can now benefit from clock domain checking. The reality is not quite as simple, but it is closer to that than you would expect it to, because we have designed Hardcaml in this very specific way of like keeping it compositional and decoupled. So that's sort of a powerful design philosophy.
Thank you.
Yeah.
Alrighty, we'll have to leave it there. Let's thank the speaker again. Cheers. Thanks, Rachit.